Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, we're going to bring on Professor Walter Alvarez of Berkeley. He made world history years ago when he and his father came out with the heretical revolutionary theory that an asteroid killed the dinosaurs. And since then, he's gone on to create what is called big history, looking at history through a different lens, the lens of science and geology and astronomy, to explain events that happened in human history that otherwise seem pretty random. And so once again with us today is Professor Walter Alvarez, author of a new book, A Most Improbable Journey, A Big History of Our Planet and Ourselves. And if you want to know more about Walter Alvarez, plus more about what I'm doing, go to my website. It's mkaku.org, mkaku.org, and it lists 3 New York Times bestsellers that I've written: The Future of the Mind, which talks about telepathy, telekinesis, and all the revolutionary developments as we physicists begin to probe the secrets of the living brain. Also, Physics of the Impossible, talking about time travel, space warps, talking about teleportation. And also the future of Physics of the Future, talking about the next 100 years in science, artificial intelligence, robots, space travel, all of that in my book, Physics of the Future. But once again, today we're talking to Walter Alvarez. We should also point out that not only is he a professor of geology at Berkeley, but his late father was Louis Alvarez, winner of the Nobel Prize in Physics. And the father and the son made a heretical theory several decades ago, because way back then people thought that the dinosaurs died because the weather changed. Maybe it got too hot. If you saw, for example, Walt Disney's version of Igor Stravinsky's famous symphony, Walt Disney conjectured that it got hot. As a consequence, the dinosaurs died because of a tremendous drought. Well, Professor Alvarez and his father were not satisfied with that theory and proposed that a gigantic asteroid from outer space plowed into the earth, killing the dinosaurs because sunlight was darkened because of all the soot that went into the air. Well, some people thought that was a bunch of junk, a fantasy by physicists. People thought that what killed the dinosaurs was much more complex, not just a single blow from outer space. But since then, we have actually found the asteroid crater. It's in Mexico, in the Yucatan of Mexico. In fact, if you look at maps of the Yucatan, you'll see that there's a bullseye, a gigantic crater 180 miles in diameter, a ring which marks the original crater which created the cataclysm which wiped out the dinosaurs. Well, since then, Walter Alvarez has gone on to create something called big history. That is looking at events today that were shaped hundreds, thousands of years ago. A simple example would be the Ice Age. Look at the fact that we have the Great Lakes. We have Salt Lake City. We have the shape of the United States itself that was shaped by the Ice Age. And so you realize, therefore, that events that took place in modern American history can be traced back to a geological event that happened 10,000 years ago. Or look in outer space at the moon. The moon was blown out of the Earth about 4.1 billion years ago, according to the latest theory. The moon, in turn, helps to stabilize the spin of the Earth. Otherwise, the Earth would have flipped over billions of years ago, and we wouldn't be here today. And so, again, an event that took place over 4 billion years ago. An asteroid slams into the Earth and creates debris which condenses into the moon. That event helped to stabilize the Earth, and that's why we're here today. If it wasn't for that event, then the Earth would not have a moon, the Earth would have tipped over billions of years ago, and we wouldn't be here to talk about this. And so that's called big history, the fact that you can look at history through a different lens. You know, historians, when they look at history, oftentimes see a random series of events. Well, maybe, maybe not. But these random series of events actually have a basis in history. When you look genetically at humans, you realize that we are all very closely genetically linked together. The only way to explain it is to assume that humanity was almost wiped out 70,000 years ago, and only a handful of us that were genetically very similar repopulated the entire Earth. And so here's a brilliant example of a theory that has both geologic and biologic evidence. We have both the geologic evidence that there was a volcano that erupted 70,000 years ago, and we have the biologic evidence that, yes, only a few hundred of us perhaps, survived a cataclysmic event 70,000 years ago. Now again, it's just a theory, but it's perhaps not a coincidence that two cataclysmic events both happened 70,000 years ago to shape the nature of humanity itself. And so that's big history. The fact that you can look at history through the lens of physics and geology. Another example that is mentioned in the book is the fact that, well, we all speak English. Now, of course, everybody knows that we speak English in the United States, but by rights, we should have been speaking Spanish. It was the Spanish that colonized the New World, not the British. And so what caused the reversal of fortunes? Why don't we speak Spanish? Why do we speak English in the United States? And it all goes back to Queen Elizabeth I and the Battle of the Spanish Armada. Back then, the Spaniards had perhaps the greatest seafaring fleet of all time. It was called the Spanish Armada. It was to be the fleet that would allow the Spanish to rule the world. They pretty much conquered Mexico. They conquered Latin America. Next, they were going to conquer North America as well. But there was a problem, and that is, well, the British had their designs on North America. And so there was a battle between the Spanish Armada and the smaller forces of Queen Elizabeth I. Now, history books say that the forces of Queen Elizabeth I won because of ingenuity, daring, smarts. They won the battle even though they were outgunned, and as a consequence, the British began the colonization of North America, the colonization of the United States, leading to the fact that we speak English here in the United States. Well, big historians say, not so fast, not so fast. If you look in detail concerning the battle of the Spanish Armada, you begin to realize that events that took place thousands, millions of years ago helped to determine the shape of that battle. And so, well, we'll leave it to Walter Alvarez to elaborate on this. But yes, it turns out that events that took place thousands, millions of years ago did in fact help to tip the tide, which meant that the forces of Queen Elizabeth I defeated the Spanish, and that's why we speak English here in the United States. Amazing. So there are many other facts which I think are quite interesting about how science affects the course of history. Another example would be, well, if you saw the movie The Imitation Game, you realize that the British cracked the German code. As a consequence, during World War II, the Americans and the British knew exactly what Hitler was planning because we read their cables, and it was science, the science of mathematics, which led to the cracking of the German code, and that's why we don't speak German here in the United States. Okay, well, let's take a short commercial break. Once again, our special guest is Walter Alvarez. The book is called The Most Improbable Journey, A Big History of Our Planet and Ourselves. So stay tuned as we talk about history through the lens of geology and physics.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic Fantastic with Professor Michio Kaku. In this hour, we're going to talk about a new book called A Most Improbable Journey, about something that's new. It's called Big History. And it's about how science, the science of the Big Bang, the science of geology, the science of physics, how they shape not just the Earth, but human history as well. And with us today is Professor Walter Alvarez, a professor of geology at the University of California at Berkeley. And I should mention that I got my PhD at the University of California at Berkeley way back in 1972. Anyway, he's with us today to talk about his new book, A Most Improbable Journey, a big history of our planet and ourselves. We should also mention that he's the best-selling author of T-Rex and the Crater of Doom. And with he and his father, Louis Alvarez, who won the Nobel Prize in Physics, they pioneered the theory that an asteroid plowed into the Earth roughly 65 or so million years ago, which helped to contribute to the demise of the dinosaurs. So, Professor Alvarez, glad you could be on Science Fantastic.
Pleasure to be here.
Okay, the first question we always ask our guests is, how did you, as a youth, when you were a kid, what steered you in the direction of becoming a scientist?
Well, I came from a family that had been medical research doctors, and as you mentioned, my father was a physicist, so it was kind of always fairly probable that I would be a scientist. But I also like the outdoors. I like to be out in nature. I like to be walking around in the mountains. And so I wasn't really interested in being a laboratory scientist. And geology really appealed to me. And boy, what a great choice. It's it's a wonderful career, and I just love it.
Okay. And as I mentioned, with you and your father, you proposed a theory that contradicted previous theories about the dinosaurs, claiming that a gigantic asteroid plowed into the Yucatan of Mexico 65 or so million years ago. How has the theory held up? I understand that there are expeditions now to the Yucatan to try to actually retrieve fragments of that asteroid or comet. But how has the theory held up?
Well, the theory came out in 1980. We proposed that an impact of a large asteroid or comet would have made environmental disruptions that would have done in the dinosaurs. And it was very controversial for the first decade or so. And then in 1992, the crater that you mentioned on the Yucatan Peninsula in Mexico was discovered, and it dates at exactly the same time as the dinosaur extinction. In fact, you can even see at the level in stratigraphic record around the world, at the level where the extinction took place, you can find debris from Yucatan all over the globe. So I think it's fair to say that there's really very little question any longer that the impact in the Yucatan was responsible for that extinction. There continues to be interesting research going on because there was also a large volcanic event in India, more or less at the same time, and we're trying to understand now how the extinction could possibly be related to both a volcanic eruption, which is questionable, and an impact, which is quite definite.
Okay, and I understand there's another theory which says that the impact was so great that it sent a shock wave through the planet Earth, which then destabilized the crust in India, perhaps resulting in the volcanic eruptions there. But who knows? Anyway, let's move on because we want to talk about your book. Your book is called The Most Improbable Journey, a big history of our planet and ourselves. So first of all, let's talk about what is big history.
Big history is the idea that maybe it would be interesting and useful to think about everything that has happened in the past, all the way back to the beginning of the universe with the Big Bang, and continuing on until you get to us right now. So it's an attempt to tie together human history with the historical sciences that try to find out what happened in the past, like astronomy and cosmology and geology and paleontology, archaeology, biology, All of those sciences are now in the process of learning more and more about what happened in the past. And so big history is the attempt to see all of that as a unified field. It's a way of breaking down the specialization that is inherent in pretty much all of the classes that we read about history and all of the books that we read about history.
Okay, well, when I was in elementary school, I had a kind of a dumb question, and that is, why do we speak English? I mean, why don't we speak Spanish? Because, of course, the Spaniards were the ones who began the colonization of the New World. And then I learned that there was a battle between the Spanish Armada and the forces of Queen Elizabeth I. And, well, the British won, and that's one reason why we speak English. But you link that up to big history. So could you elaborate on that?
Yes, the thing that fascinates me is how different events that took place long ago in the history of the Earth or the history of the cosmos have set the stage on which human history has unfolded. Or how geological events can influence human events. So the case that you mentioned, the case of the Armada, is particularly interesting. The Armada was a great Spanish fleet that was intended to transport the Spanish army from Belgium over to England to try to bring Protestant England back to Catholicism. And the first point is that the English Channel had to be crossed, and the English Channel is only there because of events that happened during the Ice Age, the particular way in which the Ice Age unfolded and allowed there to be that channel between Great Britain and Europe. But then there's another interesting effect, and that is that the Armada was anchored off the coast of Belgium, waiting to pick up the Spanish army. And one night, the wind was blowing from the sea toward the land, toward the Spanish fleet. So the English set fire to some old ships and let the wind carry them into the Armada. And although they didn't actually set any Spanish ships on fire, they so disorganized the Spanish fleet that ended up being the end of the attempt to conquer Britain. And that's why England remained Protestant and did not become a Spanish-speaking country and Catholic.
And that in turn, well, the rest is history, as they say, given the fact that began the decline of the Spanish Empire and the rise of the British Empire. And in part, that's the reason why we speak English rather than Spanish.
Yeah, and to me, one of the interesting things about it is what we call contingencies, things that did happen but might very well not have happened. So, for example, if the wind had not been blowing towards Belgium on that particular night, the whole history of the world might have been quite completely different. And that's what lies behind the title of the book, A Most Improbable Journey, in the sense that the way history unfolded is so totally improbable when you consider all of those little contingencies that it's really quite amazing that we live in the world we do and not in some other worlds.
So I hope when you read the book, A Most Improbable Journey, A Big History of Our Planet and Ourselves, you look at history in a totally different way, that events that took place hundreds, thousands of years ago impact on today's history. That's called big history. at the University of California at Berkeley. The book is called A Most Improbable Journey, A Big History of Our Planet and Ourselves. Well, before we continue, let me just say that you can always go to my website, mkaku.org, mkaku.org, to find out what I'm up to, or go to my Facebook site, Michio Kaku. In fact, we have now 3 million fans on Facebook, or you can pick up my Twitter feeds. We have 500,000 people that pick up the Twitter feeds. Well, where we last left off, we were talking about how events that took place thousands of years ago into the past affect things today. Now, recently I was having some dinners with my friends from Italy, and they mentioned the fact that their relatives were affected by that horrible earthquake that ravaged central Italy. And Walter, according to your book, perhaps the earthquake that affected Italy and other events in Europe were also shaped by events that took place thousands of years ago. Could you elaborate?
Sure, but let's change our time scale. We're really talking about millions of years ago, because Earth's history is just almost imaginably long. But here is a fascinating thing that happened in Earth history, and which is responsible for all of those Italian friends that you had dinner with. So imagine that you're looking at a map of the Mediterranean, and off on the west is Spain, and in the center is Italy, and halfway between them are the two big islands of Corsica and Sardinia, which are sort of aligned north-south. Well, we know from geological evidence that maybe 30 million years ago, those two islands were up against the south coast of France. And they have gradually rotated around as a block. They are a tiny geological plate, and they have rotated around, and they collided with a submerged oceanic plateau in the place where Italy is now. So there was no Italy above sea level at that time. But when those two islands rotated around, they collided with that plateau, and they pushed up the mountains of Italy, the Apennine Mountains, which is where those earthquakes that you mentioned have just been taking place. And so that's why Italy is there. It's only there because of the rotation of Corsica and Sardinia. And so that's why there is an Italy. And if those islands had not rotated, there would have been no Roman Empire. There would have been no Roman Catholic Church. There would have been no Italian Renaissance. There would have been none of those friends that you had dinner with, and history would have been entirely different. And so the point is that Earth history in the very far distant past has set up the stage on which human history has unfolded.
So you're trying to tell me that events that took place millions of years ago, in some sense, shaped the entire course of European history, the rise and fall of the Roman Empire, all of that linked to these geological events millions of years ago. Is that what you're saying?
That's exactly right. And let me go back further. I should also say that for most people, hearing geologists talk about millions of years, it sounds terribly, terribly long ago. And in fact, it is. But the way geologists think is that a million years is our basic unit of time because of Earth history being so long. But let me tell you about something that happened billions of years ago, because Earth was formed 4.5 billion years ago. And early on in the formation of the Earth, we were hit by a truly large impacting object, something the size of Mars. And that impact knocked off a big chunk of the outer part of what was then the growing Earth, and that became the moon. And so we have this moon out there, this very large moon, which is unusual in the solar system. And that moon acts as a stabilizer on the Earth. So what it means is it keeps our rotational axis, the North Pole, aligned pretty much where it is right now. And if we didn't have the moon out there stabilizing our rotation, then Earth's rotation might have been quite chaotic. The seasons would have been very strange and coming and going, and it would have been a very less attractive place for life to have appeared and life to have developed into what it
Okay,
is.
Walter, we're going to have to take another short commercial break. But after the break, we're going to continue a discussion of big history, how cosmological, astronomical, geological events millions of years ago has shaped the history of humanity today. Once again, our special guest is Professor Walter Alvarez. The book is called The Most Improbable Journey, and you are listening to Science Fantastic. Give us a call at 866-323-2129, and you can share your thoughts on over 100 radio stations that carry Science Fantastic. So stay tuned.
This is Science Fantastic. For more information on this and other great talk programs, go to talkradionetwork.com.
Hello, my name is Roy Masters. I'm an English veteran who's been witness to history and proud to become an American citizen. Because in America, free thought was encouraged and being truthful mattered more than being nice. My America was truly politically incorrect in all the best ways, which is why we were blessed. But things have changed, and Americans don't think American anymore. Even though I still speak with an English accent, my heart thinks American. My voice speaks American, and that is freedom. Please join me on my daily radio show Advice Line, Monday through Friday, and I will help you to reclaim our country. Let me help you find the courage to think and speak American again. Please download my radio show app, available now at the Apple App Store and Android Google Play. Thank you.
The Foundation of Human Understanding is a 501c3 church.
I'm Jim LeBlanc with Volunteers of America. When it comes to advertising, you gotta call Dan.
I'm Mark Jones with SunPro Solar. If you're not getting a significant return on your advertising investment, you gotta call Dan.
I'm Blair Cottingham with United Rentals. If you're not happy with the results of your advertising, you gotta call Dan.
Generally, we work with two types of clients. Those who advertise and are worried about their return on investment, or those who are frustrated about not getting a better return on investment. You probably don't fall into either of these categories, but if you do, call me. I'm Dan Glaviano.
If you spend $10,000 to $80,000 a month on advertising, Dan will show you how to make your advertising a profit center, not an expense. Dan only works with one business in any given category. Find out if your category is still available. Visit gottacalldan.com. gottacalldan.com. That's gottacalldan.com.
Do you worry a lot? If you're forgetful, nervous, moody, or overwhelmed, chances are you're not protecting yourself from the ravaging effects of stress and anxiety. No matter the cause, ongoing stress and elevated levels of the stress hormone cortisol can rob your memory, your health, your quality of life, and your future. Now you can combat the effects of stress and anxiety while improving your memory and recall at the same time with the dietary supplement Calm and Clever. Studies show that the ingredients in Calm and Clever reduce cortisol by as much as 30% in as little as 1 to 2 weeks and increase your ability to recall facts, names, and numbers in 4 to 12 weeks. Calm and Clever was created by scientist Kurt Hendricks, a principal investigator in 2 NIH-funded studies on Alzheimer's disease. Try Calm and Clever for 2 months. You'll feel the difference. Call 1-800-758-8746 or go to calmandclever.com.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Professor Walter Alvarez, best-selling author of books like T-Rex and the Crater of Doom. His latest book is called The Most Improbable Journey, a big history of our planet and ourselves. And so once again, Walter, for those people that may have just tuned in, what is big history?
Big history is the attempt to see everything in the past which has led to us as human beings as a unified field of study. It breaks through the specialization that most books and courses about history have. And I find it extremely exciting in that way because I like to see how things tie together. and I think many other people do. I taught a course about big history for 5 years here at Berkeley, and the students I had were so excited to be able to see how all of their specialized courses that they've taken, how those courses fit together and to really understand the big picture. So let me tell you just briefly something that's very exciting about big history. It was really invented by a man named David Christian, who is a historian in Australia. And David Christian did a set of video lectures about it. And one day in Australia, he had a telephone call, and a woman with an American accent said, "Professor Christian, would you be willing to take a call from Bill Gates?" Well, David was very happy to take a call from Bill Gates. And it seems that Bill Gates of Microsoft had seen those video lectures and thought, wow, this is something that would really excite students in the 9th grade at a time when so many students are starting to lose interest in learning. And so Bill Gates and David Christian started something called the Big History Project. And if you look that up on the web, you'll find all sorts of information. And it's turning out to be very exciting to 9th grade students, and probably will be coming to a school close to you in the near future.
Okay, well, let's be specific about big history. Let's talk about fire. Some people say that one of the defining moments in our evolution on the earth was when we harnessed the power of fire, which no other animal on the earth can do. How does that relate to big history?
I find the history of fire to be quite fascinating. As you say, it seems to be a characteristic of humans and of no other species that we make intentional use of fire, and we have really mastered the use of the fire to the point even where we could send a space shuttle into orbit on a great column of fire. And so we know how to do a lot of stuff with fire, but here's the fascinating thing about it from a big history standpoint. Did you know that most of Earth's history had to pass before there could even be fire anywhere on the Earth, natural fires or human fires? And the point there is that fire occurs when oxygen in the atmosphere combines with a fuel like wood or coal or oil. And there wasn't enough oxygen in the Earth's atmosphere until fairly late in Earth's history.
Walter, we're going to have to take yet another short commercial break. But after the break, we're going to continue our discussion of big history and fire and the evolution of humanity itself.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Walter Alvarez, Professor of Geology at the University of California at Berkeley, best-selling author of T-Rex and the Crater of Doom. His latest book is called The Most Improbable Journey, A Big History of Our Planet and Ourselves. And just before the break, we talked about fire. And as I mentioned, some people think that our harnessing of fire is one of the pivotal events in our history, but that in turn was made possible by events that took place literally billions of years ago. So, Professor Alvarez, could you elaborate?
Sure. As I was saying before the break, most of Earth history had to pass before there was even the possibility of having fire on the Earth. And there really were three things that had to happen before we could have fire. The first one is that bacteria had to figure out how to do photosynthesis, use the energy from the sun to make their plant material, and in the process they give off oxygen as a waste product. So that's the first thing. But even after the bacteria could make oxygen, it would not accumulate in the atmosphere because the Earth had so much iron around, and that iron would be rusted by oxygen in the atmosphere. And there was a huge amount of iron, so it took a long, long time before there was oxygen left over from that rusting process to accumulate in the atmosphere. So now we have oxygen in the atmosphere, but still all life is below sea level, and so nothing could burn until the plants figured out how to emerge onto the land, and you started to have wood and then coal, and that could burn. And all of those three processes took up about 90% of Earth history. So now we have fire, and we can do all sorts of things with it. But for most of Earth history, you could not have had fire.
Okay, and let's just say a few things about the Ice Age that ended about 10,000 years ago. If you look at a map of the United States, you see the Great Lakes, you see the Great Salt Lake, all of which are remnants of the receding of the glaciers 10,000 years ago. So how does that link with your theory about big history, the Ice Age?
I think in addition to the lakes you mentioned, there's another thing that you see on the map of the United States, and that is the Ohio River and the Missouri River flowing, one of them west and the other one towards the east and emptying into the Mississippi. And those two big rivers are more or less where the last ice sheet ended. They marked the limit of the great ice sheet that covered Canada and extended into the U.S. So imagine if there had been less ice, then those rivers might have been in Canada, and there would have been no easy way to for people from the 13 colonies on the East Coast to explore and settle the middle of the country. So my colleague Steve Dutch at the University of Wisconsin in Green Bay has pointed out that all of the history of our development of the Midwest and the Western U.S. is dependent on how far the ice sheets got about 10,000 years ago.
And so, in other words, American history is basically, to understand American history, you have to look at events that took place thousands to millions of years ago, beginning with the Ice Age, right?
Yeah, you do. And most historians think of the Earth as this kind of neutral stage on which history has unfolded, and they just take it as a given that the rivers are where they are. But for geologists like me, that stage has its own history, and it's quite fascinating to see what historical events have produced the world that our history has taken place in.
Okay, and also let me give you a teeny-weeny example of big history. I live in Manhattan, where we know that we have tall buildings in Lower Manhattan, tall buildings in Midtown, but that's it. All the skyscrapers are concentrated either in Lower Manhattan or Midtown, but nothing in between. And the reason is, well, because of the formation of Manhattan millions of years ago, the lava flowed in the shape of a U. And so in order to drill a skyscraper, you have to have bedrock, and there are only two places in Manhattan where you can reach bedrock, and that is Lower Manhattan and Midtown. So the very shape of New York City was determined by events that took place millions of years ago when the volcanic eruptions basically determined the shape of the bedrock underneath Manhattan. And that's why we have skyscrapers.
That's exactly right. And I used to live in New York or near New York City, and what you're saying is exactly right. And so let me say that that's pretty good geology, Professor. And any time that you decide that you're tired of physics, we would be delighted to have you join us as a geologist.
Okay. Well, I work in another phase of big history. I work on the Big Bang. And in your book, you mentioned that there are 4 phases of big history, starting with the Big Bang. And so in some sense, I work on big history, except from the point of view of a physicist.
Well, that's right, and it's a fascinating part of big history to try to understand how the universe was set up during the Big Bang. We've no idea why, but that's when all of the laws of physics were set into place upon which everything depends that has happened ever since.
Right. And when I was a grad student at the University of California at Berkeley years ago at the RAD lab, I realized that all the work that we were doing with subatomic particles basically determined the shape and the nature of creation itself, the nature of the Big Bang, the way in which the elements were created, the formation of the Earth out of the elements, and all of it came from physics and the Big Bang. Okay, well, we run out of time, so once again, our special guest today has been Professor Walter Alvarez, and the book is called A Most Improbable Journey, A Big History of Our Planet and Ourselves.
This is Science Fantastic. Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, well, once again, you can get on Science Fantastic by giving us a call at 866-323-2129. So let's move on and take the first listener phone call.
Yes, my name is Lynn from Petoskey, Michigan. I listen to WMKT. My question is, do you think all the building, which affects vegetation and aquifers and interferes with the cooling, natural cooling of surface temperatures of the Earth, affects the climate? After doing wildlife photography for decades, I feel that it does. People always talk about the ozone. Everybody's looking up at the sky. Do they ever look down at the ground and see that surface temperatures are heating up? Microclimates in cities can be, several dozen different types because of so much heat from all the overbuilding. Thank you.
Well, you raise a very interesting question, which is actually factored into the computer programs. If you listen to the news, for example, on the car radio, as you drive away from a city, you get a feeling of the temperature in the city and the temperatures outside the city, and you realize that they differ by about a degree. I live in New York City, for example, and whenever I get the news reports from the suburbs and from Manhattan itself, I realize the difference is about 1 degree Fahrenheit. Why is that? Because of all the heat generated by the city, not just in terms of cars, but also in terms of home heating and industrial heating. And the combination of all these factors raises the temperature of the cities. However, that can be factored in the computer program. We know, for example, the surface area of all the cities on the Earth. We know the average amount of what are called joules of energy released per square foot of real estate, and we multiply, and we can calculate, therefore, the total amount of energy that is put into the atmosphere coming from the cities. So that is factored into the computer programs. I should also point out that that is not the major contributor to the fact that the Earth is warming up. By the way, even the skeptics of global warming admit that the Earth is heating up. The debate is over the question of how much comes from human activity versus natural cycles. But in terms of the cities, yes, you can actually see it, measure it, and factor it into computer programs that the cities are slightly warmer than the suburbs and the countryside, and that does contribute more to the warming of the planet Earth. But most of the warming, we think, comes from carbon dioxide in the atmosphere. In fact, one thing you can do is to run the videotape backwards. If you take the computer programs of today, with all the known chemical composition of the Earth's atmosphere, and then let the computer go backwards in time to check to see whether it can reproduce the temperature of the past, you find out that it can indeed. So these computer programs can run forward or backward, which gives us the feeling that they are, in fact, scientifically credible. Okay, well, let's move right along to the next listener phone call.
Hi, Dr. Kaku. This is Scott Millard from Tucson, Arizona. I listen to your shows mostly on the Internet. I was wondering, is it possible, since it has been theorized that the universe consists of 11 dimensions, that the reason we can't see black matter or detect black energy is that because they exist on one of the other planes of existence that we do not perceive. Thank you.
Well, your theory is actually not far-fetched at all. In fact, one of my colleagues, Professor Licken, at the Fermi Lab outside Chicago, has actually proposed this as a viable theory of dark matter. So let's break down your question into its parts. We believe that there is a unified theory that explains the Big Bang. The latest version is called string theory. And string theory and membrane theory allow for 11 dimensions. Now, we think that our world exists in 3 dimensions with length, width, and height, and Einstein adds time as the 4th dimension. However, in a 4-dimensional world, there's not enough room to accommodate all the forces. We have light, we have the nuclear force, we have gravity, and if you put the equations of all these forces together, 3 dimensions is simply not big enough to accommodate all these forces. When you go up to 11 dimensions, bingo, all the forces unify very nicely, almost by magic. All the equations work perfectly in 11 dimensions. And as you pointed out, there is something called dark matter. Dark matter is invisible matter, but it has gravity. In fact, it holds the galaxy together. So we need dark matter in order to hold the Milky Way galaxy together, or else the galaxy would have flown apart billions of years ago and we wouldn't be here. But what is dark matter? We don't know. If you want to win the Nobel Prize in Physics, figure out what dark matter is. It's 10 times more plentiful than ordinary matter. It has gravity, but it is invisible. If you had dark matter in your hand, for example, it would literally sift right through your fingers, right through the atoms of your hand, go right through the crust of the earth, go all the way past the center of the earth, all the way to China, and it would reverse direction in China because it has gravity, and come all the way back to New York City. So dark matter, as you can see, is an incredibly strange form of matter, but it makes up most of the universe. Well, as I mentioned, one of my colleagues, Professor Joe Licken at Fermi Lab outside Chicago, has a theory that perhaps, as you pointed out, there are other planes of existence, and perhaps dark matter exists on a parallel universe. Take 2 sheets of paper. On the bottom sheet of paper, put our universe, the universe of atoms that we are familiar with. You, me, our family, our cities, the earth, on 1 sheet of paper. Above the sheet of paper, there is a parallel universe, and in that parallel universe, put dark matter. Now, we on the lower universe cannot see the higher universe because it hovers above us in another dimension. 2 parallel universes that don't interact. But gravity goes between universes, because gravity, according to Einstein, is nothing but the curvature of space. Therefore, dark matter's gravity will go between universes, even though dark matter itself cannot. Now, if you're on our universe, what will you see? First, you will see nothing, because dark matter hovers above us in a parallel universe. Light goes underneath this other universe, so you cannot see dark matter, but you can feel its gravity. So it would be A, invisible, because it hovers above us in a parallel universe, and B, we would feel its gravity. Well, what is dark matter? Exactly that. Now, therefore, Professor Licken proposed an alternate theory of dark matter, and that is dark matter is ordinary matter hovering above us in a parallel universe, one of the other 11 dimensions that we think exists. I should also point out, however, that the leading theory of dark matter is not that. The leading theory of dark matter is that it's another vibration of the string. I work on string theory. I'm one of the pioneers of the subject, in fact, and we believe that all matter consists of vibrations of tiny strings. Dark matter could be another octave of the string.
This is Science Fantastic.
Write to us. Give us a call at 866-323-2129. You'll get a recording. Add your name, the call letters of the radio station, and the city you're calling from. And hey, perhaps you can have your thoughts heard on over 100 radio stations that carry Science Fantastic. Once again, it's time for your phone call. So let's take the next listener phone call.
Hi, I was just wondering if you had any opinion on the recently popularized theory that reality is only a simulation.
Well, yes, that theory has been kicking around, and it's been getting some comments because, well, we physicists have to answer the question. Here is a theory. Is it true or not? Or does it make sense? The theory is that perhaps we live in a computer simulation. For example, if you watch a movie, the movie actors act as if they're real. They have their lines read, so they have emotions and there's a plot. But we know it's fake. It's all just a simulation of reality. Well, computers get very, very good over time. And everyone has seen the movie The Matrix. And in the movie The Matrix, well, yes, it takes that nightmarish vision to its logical conclusion, and that is the reality itself is an illusion, that we live in a computer program, just like in the movie The Matrix. In the movie The Matrix, if you haven't seen it, the aliens have taken over from humans, and they put us in pods and use us as batteries for their engines. But they put an electrode into our brain, which gives a computer program, a virtual reality computer program that looks pretty real. So everybody you know, the job you have, the things that you do, it's all fake. All fake because it's nothing but a computer program that's being run. Now, what do physicists say about this? First of all, we physicists try to simulate things like the weather. It turns out the weather is a quantum mechanical object with trillions and trillions of atoms, but a computer will simply not be big enough to model all the atoms of the weather. It's simply a project that is too big for our biggest computers. So then the question is, how big would a computer have to be to do this simulation? Well, we have now something called chaos theory. And in chaos theory, we began to realize that, hey, the weather really is very difficult to simulate. In fact, the smallest object which can simulate the weather is the weather itself. At that point, you might say, well, that simply means it's impossible. If the smallest object that can simulate the weather is the weather itself, then it means that the weather cannot be simulated. Now, of course, the Earth and reality is much bigger than the weather. And so then the question is, can the universe be simulated as a computer program? Well, the short answer is we don't know. Probably not, but there's no proof that it can't be that way. Now, can the universe be a motion picture, and we're simply actors acting out in a motion picture that's already been filmed, and we're acting as if it's real, but of course it's not? Well, we have something called quantum mechanics. And in quantum mechanics, there's uncertainty, that you cannot really predict the future. So even if you have a gigantic computer, you cannot accurately predict the future evolution of atoms because of the fact that everything is quantum mechanical. Therefore, personally, I believe that the universe probably cannot be a simulation for those reasons. First, the smallest computer that can simulate reality is reality itself. And second of all, we have quantum mechanics, which says that the future cannot be determined, and therefore it means that most likely we do not live in a simulation. Now, is that a proof? No. So there's still active debate, even among physicists, about whether or not we live in a virtual reality movie. In other words, perhaps everything that we see around us is on a CD-ROM. God puts the CD-ROM into his cosmic computer, and God hits the play button, and here we are talking about Science Fantastic. Well, as fantastic as that could be, You cannot rule it out, even though I personally do not believe in that theory. Okay, let's move right along to the next listener phone call.
Hi, my name is Laura Spring. I'm calling from Great Falls, Montana. I was just wondering, so like people talk about a lake flipping, so like the cold water going to the top and the hot water going to the bottom. I was just wondering if that's true, and if so, like why does it do that? How does it do that? You know. Bye.
Well, you ask a very interesting question that affects everybody that has a house. It has multiple stages. You know that the temperature in the top of a house is warmer than at the bottom of the house because we know that hot air rises. And, of course, we'll talk about why in a moment. But hot air rises. That's why the temperature is hotter at the top of a building than the bottom of a building. And the same thing works for water. Water gets colder the further you go down into water. And the question is why? And the answer is, believe it or not, everything is made out of atoms. So air is nothing but atoms in motion. When you heat up air, the atoms move much faster. They have more energy, and therefore they tend to expand. That's why warm air expands. You see that in weather balloons. You see that in when people go ballooning. You put hot air into the balloon and it makes it rise. Why? Because everything's made out of atoms. More energy means that they expand to take up more space, and that's why hot air rises to the top of your building.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Okay, well, moving right along, let's take the next listener phone call.
Hello, this is Big Al from Chattanooga, Tennessee. I listen to you on FM 102.3. My question is, in the reference to the color of the sky and the sea, isn't the ocean or the sea just a giant reflector, as if the sky turned red for some reason? Wouldn't the ocean also appear that color? Thank you.
Well, the answer is yes, but that's not the primary reason why the ocean has a certain color. Many people notice that the sky is blue, the oceans are blue, and therefore they say that, well, since water has no color, the blue of the oceans is due to the fact that it reflects the light from the sky. Well, not so fast. If you actually look at why the sky is blue and why water is blue, you find out something a little bit different. First of all, it was Lord Rayleigh, the famous British physicist, who 100 years ago finally figured out why the sky is blue, but the sunset is red. And that is when light goes through air, it scatters. Because you're always looking away from a light bulb, you're looking away from the sun. You're looking at scattered light when you look around the room. And blue light scatters more than red light. Red light scatters the least, blue light scatters the most. Now, if you don't believe me, simply turn off all the lights in your room. And immediately you can't see anything because you are staring at reflected light when you look around the room. And blue light scatters the most. Okay, well, let's take a short commercial break, and after the break, we're going to continue a discussion of science and why the sky is blue and why the oceans are blue.
This is Science Fantastic. You're listening to Science Fantastic with Professor Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we take your phone calls and put them on air. So give us a call. The hotline number is 866-323-2129. Well, before the break, we had a very simple but profound call, and that was, well, why is the sky blue? And is that the reason why the oceans are blue? Is it all nothing but reflected light? And the answer is, well, partially, but it turns out that the sky is blue and water is blue for a different reason. It turns out that Lord Rayleigh, a physicist about 100 years ago, figured out that blue light scatters the most, while red light scatters the least when it goes through air. Therefore, when you look at the sunset, you're looking through a large amount of air for the light to go from the sun to your eyeball at sunset. When it's daytime, it's noontime, for example, light goes right through the atmosphere, and so you have a shorter distance. The longer the distance that light travels, the redder it gets, because all the blues scatter away. That's why the sunset is red, because red light will go through long distances without scattering so much. While at noontime, it turns out that light could go right through the atmosphere very quickly, and there's not much air for it to go through. Therefore, it scatters the least, and therefore you have blue. Now, it turns out that water has a vibration of its molecule. It's H2O. It vibrates like a boomerang. And as a consequence of the vibration, it absorbs light, just like the scattering of light that I mentioned. That's why water, believe it or not, is slightly bluish. That's right. You can actually show in the laboratory that water is slightly bluish because of the fact that it will absorb radiation at a certain frequency, which is the frequency of the vibration of the water molecule. So in other words, to summarize, all of it comes from quantum mechanics. If you understand the vibrations that make all this possible, then you can understand why the sky is blue and why the oceans are blue and why the sunset is red. It all comes from the vibrations of atoms. Okay, let's move right along to the next listener phone call.
Yes, my name's Nathan. I'm listening from WGOW Chattanooga. My question was, what exactly is the process of building the space elevator, and is that going to be happening anytime soon? Thank you very much.
Well, a space elevator, if we could build one, would change the economics of space travel. Space travel is very expensive. Why not simply go into an elevator, hit the up button, and go into outer space? Now, that sounds outrageous, but it is within the laws of physics. In fact, it was the famous Russian physicist Tsiolkovsky who first proposed a space elevator, and we'll talk about it more after the break. A space elevator that could change the destiny of humanity if we could only build one.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. You're not going to get a busy signal. You get right to us 24/7, anytime, day or night. You can call the number 866-323-2129. Leave your name, call letters of the radio station you're listening to, and the city you're calling from. And hey, perhaps you can get on national radio to ask that question that's always been bothering you. Perhaps you walk down the street and you wonder, what does it all mean? I mean, the sky, the sun, the stars, the moon, how is it all put together? Well, what about the future of medicine, the future of space travel? All of that we discuss here on Science Fantastic. Okay, well, first of all, I neglected to finish the question that came in earlier about the space elevator. Let's do that, and then we'll jump right into the fourth dimension. First of all, a space elevator is a long tube that goes from the Earth into outer space. It's like a string, and it spins because the Earth spins on its own axis, and it doesn't fall down. It's sort of like Jack and the Beanstalk. What keeps the beanstalk from falling over? And the reason is because the Earth spins, and it's like having a ball on a string. If you have a ball on a string and you spin the ball, why doesn't it fall? Because of centrifugal force. And so the centrifugal force of the ball spinning around the string is the reason why the ball doesn't fall, and it's also the reason why a space elevator would not fall at all. Well, let's do a simple calculation. Using Newton's laws of gravity and motion, calculate the tension on a space elevator, basically a string so long that centrifugal force prevents it from falling. You calculate that the tension on the string is so great that it's greater than the tensile strength of steel. In other words, steel will snap. And that's the reason why for 100 years, even though the physics was worked out 100 years ago, physicists would shake their heads anytime someone said space elevator. Well, not anymore, because today we have nanotechnology, and with nanotubes you can actually create atomic tubes that are so tough that you can actually build a space elevator with them. So what's the catch? The catch is the world's record for creating pure nanotubes is like a centimeter or so, a fraction of an inch. So in other words, we are far away from being able to create a space elevator, even though it is within the laws of physics. So I repeat, it is within the laws of physics, but it's a practical engineering question. Once we build a space elevator, then it will change human history. We'll simply push the up button and travel just like Jack and the Beanstalk into outer space. When might this happen? I don't know. But a conjecture would be by the end of the century, we should become masters of nanotechnology to the point that we'll be able to create a space elevator. But can we do it now? The answer is no. In 100 years? Maybe. Okay, well, moving right along, let's take the next listener phone call.
Hello, Dr. Kaku. My name is Dan from New Jersey. Yeah, I do have a question about specifically about the fourth dimension that some physicists talk about. I remember a short video by Carl Sagan once where he tried to talk about the fourth dimension as a fourth spatial dimension. But then again, there are some people that say that the fourth dimension is actually time. And also, many physicists often talk about space-time as if space and time are just intimately linked. So perhaps you can help me clarify what is the fourth dimension? How is it defined? Thank you.
Well, most people understand, of course, the fact that we have 3 dimensions of space. We have length, width, and height. And when it comes to time, Einstein says that's the fourth dimension. So when we talk about a higher dimension, dimensions beyond space and time, we're now talking about the 5th, 6th, and 7th dimensions, all the way up to 11. The latest theory of physics, which is not proven, but the latest theory of physics, which many physicists are working in, is that we have 1 dimension of time and 10 dimensions of space. That would give us a unified field theory of all human knowledge. Now, can the brain visualize these higher dimensions? The answer is no. We evolved in 3 dimensions to avoid 3-dimensional tigers, 3-dimensional lions, and mammoths. We did not evolve to evade 10-dimensional or 11-dimensional beings and animals. As a consequence, we cannot visualize higher dimensions. But, hey, computers do it all the time. Your laptop computer can easily navigate in hyperspace because it's a mathematical statement. But can you, as a human, visualize it? And the answer is no. When I was a child, I used to play with this. I used to try to jump into the 4th dimension. I used to try to jump as hard as I could into the higher dimension, and I realized, even as a young kid, you can't do it. The human brain is not capable of visualizing it, even though a computer effortlessly can calculate in hyperspace. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to throw the lines open because, yes, this is your time to get on Science Fantastic. You have a question? You have a comment? No problem. Give us a call at 866-323-2129. Okay, moving right along. Let's take the first listener phone call.
Hi, Professor. This is Franz from WILK. Nanticoke, Pennsylvania. My question to you is, I've been listening to you for a while, and I don't know if this question's ever been asked, but what science fiction writers, what science fiction comic books or movies have helped you in your, in your striving to come up with string theory and other things? I would be amazed to see maybe Isaac Asimov or Ray Bradbury. But thank you for taking my question.
Okay, well, let me first of all say that string theory, which is what I do for a living, in fact, I'm the co-founder of string field theory, one of the main branches of string theory. String theory, unfortunately, is pure mathematics. So we cannot get inspirations from reading science fiction or clues into the secrets of string theory by reading science fiction or watching science fiction movies. However, I should point out that science fiction has played a pivotal role in the education and the creation of many top scientists. For example, Edwin Hubble was perhaps the most famous of all astronomers of the 20th century. He was the one who discovered the expanding universe, one of the greatest discoveries of all time. And he started out as a country lawyer in Missouri. That's right, his father was a lawyer, and his father wanted his son to be a country lawyer in Missouri as well. But, Edwin Hubble had other dreams. He was a Rhodes Scholar, got accepted to Oxford University, which exposed him to a lot of different kinds of possibilities, came back to Missouri, and he simply couldn't see himself spending the rest of his life doing small cases in a small town in Missouri. He remembered reading Jules Verne as a child. As a child, he thrilled to the stories of going to the moon and going to a comet. So what he did was he earned the ire of his father. He told his dad that, nope, he's going to quit being a lawyer and become an astronomer. He went to Chicago. He got accepted to the University of Chicago, got a PhD in astronomy from the University of Chicago, and went to the Mount Winslow Observatory and became the man who discovered the expanding universe. Amazing. He was the one who looked at galaxies. By the way, back then in the 1920s, people didn't know what galaxies were. They thought they were simply wisps of gas inside the Milky Way galaxy. He showed that no, these galaxies are island universes just like the Milky Way. Island universes in and of themselves. He calculated the velocity of these galaxies, and he found, much to his shock, that they were moving away from us. All these galaxies, he found, were more or less moving away from us, meaning that the universe is expanding. And so it was science fiction who helped to create one of our great astronomers. Or for that matter, think of Carl Sagan. When Carl Sagan, the great astronomer, when he was a kid, he read John Carter of Mars. John Carter was a fictional person created by Edgar Rice Burroughs, the very same man who created Tarzan. And it turns out that Edgar Rice Burroughs created John Carter, who is a soldier who falls asleep in a cave with gas, and he winds up on the planet Mars. Well, of course, Edgar Rice Burroughs was not a scientist and could not explain how to get to Mars. And so he simply has, in some way, the soul of this soldier being teleported to the red planet. And John Carter meets a beautiful Martian princess, of course. I mean, after all, it is a novel, Dejah Thoris. And Carl Sagan dreamed of chasing Dejah Thoris over the sands of Mars, as he wrote in his autobiography. And so he became an astronomer because of science fiction. Now, when I was a kid, I read about the works of Einstein, and I wanted to help complete Einstein's dream, his unfinished dream of a theory of everything. But on Saturday mornings, I used to watch the cartoons, and on Saturday mornings, what do they have? Flash Gordon with Buster Crabbe. And boy, I was hooked. I mean, spaceships, ray guns, cities in the sky, undersea kingdoms. What's not to love in that series called Flash Gordon? Well, it turns out that yet another dreamer was also watching the Flash Gordon series who was about my age, and that guy was George Lucas. We now know that George Lucas actually went to find who controlled the rights to Flash Gordon. He wanted to create an updated version of Flash Gordon, but unfortunately the rights were not available. So George Lucas gave up the dream of putting his childhood hero, Flash Gordon, on the big screen, and instead made a clone of Flash Gordon called Star Wars. In fact, practically scene by scene, episode by episode, you can see the similarity between Flash Gordon and the Star Wars series.
Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, well, the lines are open, so let's take the next listener phone call.
Professor, do you think man will ever figure out anti-gravity? Thank you.
Well, it turns out that, of course, anti-gravity is a staple of science fiction, but in science reality, anti-gravity is a lot harder than you realize. In fact, may not even exist at all. First of all, there is something called antimatter. Matter has a counterpart called antimatter. For example, the electron has negative charge, as we learn in school, but there's a positively charged electron called the positron. It is antimatter, and when you combine the electron with the positron, it releases energy. Now, the positron is emitted naturally by radioactive products like sodium-22. In fact, that was one of my science projects when I was in high school. When I was in high school, I actually played with antimatter. I got a Wilson cloud chamber. I got some sodium-22 radioactive source from the Atomic Energy Commission, and was able to photograph tracks of antimatter bending the wrong way in a magnetic field, proving that it was antimatter rather than ordinary matter. Now, if you say that every particle has an antiparticle, well, light is a particle called the photon. So why isn't there an antiphoton? Well, when you look in the physics book, you realize that the antiphoton is the photon. The photon is its own antiparticle. So sorry about that. There's no such thing as anti-light, which you sometimes see in science fiction novels. Anti-light is basically comes out of a flashlight, except instead of light coming out of a flashlight, darkness comes out of a flashlight. Well, sorry about that. It turns out that anti-light is light. And if you take a look at gravitons, that is particles of gravity, the antigraviton is the graviton. So anti-gravity would be gravity. Now you may say to yourself, well, this is the cutting edge of physics after all, so are there loopholes? And yes, there are loopholes. First of all, we have never seen the graviton, let alone the anti-graviton, so it's pure theory. It's pure theory that anti-gravity is the same thing as gravity. But I think most physicists would say that anti-gravity is gravity. Now, we actually want to test this with our atom smashers. If you have a beam of anti-gravity, we want a beam of anti-electrons or anti-protons. We want to ask the question, do they fall up or fall down? Think about this. This is not a trivial question. If I have anti-protons, which we can create, and anti-electrons, which we can also create in an atom smasher, put them in a bottle, and we just wait and see whether they fall up or fall down. Science says they should fall down. However, we've never done that experiment. And so it's an open question as to whether anti-gravity exists or not. Again, most physicists, myself included, would say that anti-gravity does not exist, but no one has done the key experiment allowing anti-gravity to, allowing anti-electrons and anti-protons to fall down rather than fall up. That's one loophole. There's another loophole, and that is in Einstein's equations, there are actually two terms you can put in Einstein's equations. One is the energy of space-time, and that gives us what we call general relativity, the bending of starlight, black holes, the Big Bang, all of it coming from this one term. But there's a second term in Einstein's theory, and that is the energy of the vacuum. Einstein himself thought that this was crucial for cosmology, and we think that it is crucial for something called negative energy. Negative energy, we realize just in the last few years, is perhaps the basic ingredient of the universe. 73% of the universe, we think, is made out of negative energy. Dark matter only makes up 23%. So what about matter, the stars that we are familiar with in the night sky? They make up only 23% of the universe. So in other words, anti-gravity could be in the form of negative energy pushing the galaxies apart. It could be that anti-gravity pushes the galaxies apart. But it's too small to use for a starship. It's too small to use for a hoverboard. So sorry about that. No anti-gravity in science fiction.
You're listening to Science Fantastic with Professor Michio Kaku. You're listening to Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. That's right, the lines are open. Okay, well, let's move right along and take the next listener phone call.
Hello, Professor. This is Steve. Shouldn't our nuclear plants be switching to thorium as it's safer and it's more plentiful and there's no radioactive waste? Thank you.
Well, you ask an interesting question that a lot of people have asked, and we've had such bad luck with uranium light water reactors that some people are saying, well, let's junk it and start all over again. It turns out that molten salt thorium reactors are superior, as you pointed out. For example, as just one example, the melting point. The melting point for uranium dioxide is on the order of 5,000 degrees, and that's why nuclear power plants will melt fairly rapidly. It only takes about half an hour once you shut off all the safety systems. It only takes about half an hour for a conventional nuclear power plant to hit the melting point and to create havoc in the form of a meltdown. It turns out that thorium reactors have a higher melting point, and it's more difficult to initiate the dreaded Class 9 meltdown. At Fukushima, in Japan, for example, we have not one, not two, but three meltdowns that took place 5 years ago in Fukushima. 5 melted reactors. In fact, the core is so melted is in liquefied form. But thorium, the nuclear fuel cycle, it's too late. It would cost hundreds of billions of dollars to convert to a thorium nuclear fuel cycle, so it ain't going to happen. Sorry about that. We rushed into uranium, and now we're stuck with it. We're stuck with light water uranium reactors when other designs are actually preferable. So it means that we're stuck with conventional uranium light water reactors.
You're listening to Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. That's right. Here is your chance to get on national radio to ask that question that you've always been wanting to ask. Okay, well, moving right along, let's take the next listener phone call.
This is Jonathan Logan, Chattanooga, Tennessee. My question regards Fresnel lenses.
and their applications. I've seen many videos online where Fresnel lenses are used to focus the power of the sun, usually burning wood, et cetera, and so on. My question involves third world applications like desalination of ocean water, et cetera, and so on. Could you please elaborate on some of the uses for Fresnel lenses?
Yes, I'd be glad to. First of all, Fresnel was a famous French physicist who came up with the design for a better lighthouse. A lighthouse has a gigantic piece of glass in the shape of a lens, and he thought, well, what happens if you slice the lens? What happens if you slice it? You would get lots of concentric circles. And what happens if you were to manipulate the shape of each of these slices to increase the efficiency? And sure enough, he showed that mathematically speaking, a solid piece of glass is not the most efficient way to build a lighthouse. And he designed another one. It turns out these lighthouses are superior to ordinary lighthouses because they have a very small focal length but very large aperture size. And that became what is called the Fresnel lens. More recently, people are interested in focusing light for solar power. And yes, indeed, it turns out you can increase the efficiency of a solar panel by using these slices rather than a solid piece of glass. And you mentioned another possibility, well, why not use this for all sorts of industrial applications? Well, then you get into trouble because of the fact that you have to look at efficiency and cost. And then you begin to realize that, well, yeah, you get more efficiency, but in terms of mass producing these things and perhaps helping people in the third world for desalination and stuff like that, it's sort of marginal. And so that's why there's not a big effort to do that, even though you are correct that Fresnel lenses tend to be more efficient than ordinary lenses. For example, take a look at solar power and solar energy. The big problem with solar energy is not so much the efficiency of the solar collection process. The bottleneck, you'll be surprised to learn, is storage. That's right. How do you store the energy of solar when it is dark at night and the sun doesn't shine? Or if you like wind power is great. We see a resurgence of wind power with the building of modern-day megawatt propellers. However, the problem there is, what do you do when the wind doesn't blow? The key is storage, which means a better battery. Now, it turns out that batteries are becoming more efficient, about 7% greater efficiency per year, because finally, entrepreneurs and inventors and engineers are beginning to seriously design better batteries. For example, 100 years ago or so, Thomas Edison and Henry Ford were friends, and they had a bet. What would supply the energy of the future, gasoline or batteries? Edison, of course, bet on the battery. Henry Ford bet on gasoline, and we all know what happened. But ultimately, Edison may have the last laugh, because for 100 years, there were no great inventors and entrepreneurs trying to commercialize better batteries. Now we see a stampede because people are saying there could be a gold mine out there. In fact, Elon Musk of SpaceX, PayPal, and Tesla Motors has designed a new type of battery which takes advantage of the fact that the efficiency of batteries is becoming better and better every year. And so we may see a gold rush in that direction. Now, the caller also mentioned desalination. I speak in the Middle East sometimes, and when you travel through Dubai, for example, or Saudi Arabia, you see all these fountains everywhere. However, you're in the middle of a desert, and you can imagine how expensive it is to create a fountain right in the middle of a desert. In fact, when you go to Dubai, they actually have a ski slope. That's right, you can actually ski on snow in the middle of a desert. That's how energy rich these countries are. So the problem with desalination is not necessarily the sunlight. The problem with desalination is energy and cost. It costs a ton of money to begin the process of separating out salt from water to get pure drinkable water. And so the problem there, once again, is not necessarily the sun itself. The problem is reducing the cost and the energy requirements. It costs a lot of energy to begin the process of separating out salt from ordinary salt water to extract drinkable water. And you also have to be careful about this. Australia invested billions in a series of desalination plants because they had a drought. But after they built the plants, what happened? The drought ended after 7 years. And so they had an oversupply in desalinated energy. Okay, well, we've run out of time, so that's it for Science Fantastic with Professor Michio Kaku. Good day.